So let's look at another example of non-conservative forces and the work kinetic energy theorem. So as I said, this is kind of like the diver problem. A child of mass 20 kilograms takes a ride on an irregularly curved water slide at a height of 6 meters. Okay, so that's where all our potential energy is. That's 6 meters. You should key on that immediately. The child starts from rest at the top. That's telling you what about the initial velocity? Zip, right? 0. Determine the speed at the bottom, assuming no friction is present, so no non-conservative forces. So we have the child's mass, 20 kilograms. We have the initial height of 6 meters. We've got the final height of 0 meters down here at the bottom of the slide. And we have the initial velocity. The child starts off at 0. So we're going to use energy methods again to determine the speed of the child when she reaches the bottom of the slide. So there is no non-conservative forces in effect on this problem because they said there's no gravity. So we can forget about that. Throw it out. We're going to apply the principle of conservation, though, of mechanical energy. So we're going to use our potential energy, kinetic energy relationships. All the potential energy at the top, no friction, should equal all of the kinetic energy at the bottom. So kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. So we just gathered our terms like we've done before. So back to our grassroots relationships, 1/2 mv initial squared, mgy initial equals 1/2 mv final squared plus mgy final. Okay, so we start dropping in our zeros. Initial velocity 0, we got that. 20 kilograms times 9.8 meters per second squared times the height, we've got that. 1/2 20 kilograms, velocity final squared plus 0. Now, as I'm looking at this, why didn't we do what we did before and kill off the masses? Well, we could have. We could have reduced this problem down by taking the 20 kilograms from both sides of the equation. What you do to one side, you can do to the other, because there were no other terms here. But we'll leave it for now. Just makes the numbers bigger. So we've got 1176 joules is equal to 10 kilograms, because it's halved by that 1/2. Velocity final squared. Velocity final squared then is equal to 117.6 meters squared per second squared. And we take the square root of that value. We get 10.8 meters per second. So that's our velocity at the bottom. Second part says, if the child's speed at the bottom is 8 meters per second, rather than the 10.8 meters per second, how much mechanical energy is removed from the system? So we could say, okay, we've lost 2.8 meters per second of speed. Maybe that was due to resistance. Maybe that was due to friction. So they want us to find out, well, how much of that mechanical energy was removed? It might have been friction. So we've got 20 kilograms again, 6 meters, 0 meters at the bottom. Initial velocity 0. We didn't add any push off or anything. So let's just start right with our grassroots equations. We start dropping in the values. 20K, 9.8 meters per second squared, 6 meters, doo-dah on the other side. Okay? So we get 1176 is what we had at the top, because remember, this was all potential energy. Okay, this was all the potential energy. But on the final side, on the other boundary, we said, okay, we reduced that velocity by 8. So we don't have matching energies, okay? So now we have 640 joules. So if we take the difference in those two values, 1176 and 640, we get 536 joules. That what would be lost, say, to friction or some sort of resistance. So energy can never be created or destroyed. Energy may be transformed from one form to another, but the energy total of an isolated system is always constant. The total energy of the universe is constant. If one part of the universe gains energy in some form, another part must lose energy in equal amounts of energy. And if you take some advanced courses, you'll learn about entropy and enthalpy and things of this nature that back that up. So now let's go to the next step. Okay, so we've taken our fundamental units, velocity, distance, acceleration. We develop from that force, mass times acceleration. We develop from that work and energy. Now we're going to add another component. We're going to call it power. And power is a time rate of energy transfer. Whenever anything becomes a time rate, that means you're adding a unit of time in there, typically seconds. So the average power, again, whenever you see that little hat over a letter like the P, the average power is equal to W divided by delta T, the change in T. So that's our average power. And what was W? Well, we define W as the work, force through distance, F times S, or F times delta S, or F cosine theta delta S. So the average power is equal to the work divided by the change in time, or the force divided by the change in distance divided by the change in time, or force over is times that fractional relationship. So the average velocity now in these terms can be defined as delta S by delta T, where before we said it was meters per second or something thereof. So the average power work divided by delta T then can be defined, and we just run it all the way through again, as force times the average velocity. So the average power delivered either to or by an object is equal to the product of the force acting on the object during some time interval and the object's average speed during this time interval. Okay. So the unit of power in the SI system are joules per second. And we like combining things and calling them something else. So a joule per second is called a watt. So 1 watt is equal to 1 joule per second. Remember, a joule was a Newton meter per second. Well, now we have 1 kilogram meter squared per second squared. Write this down in your notebook. Keep this handy because you may have to decompose these values and you'll need to know what cancels out and what factors out. The unit of power in the British engineering system is the horsepower. 1 horsepower is equal to 550 foot-pounds per second, or 746 watts. Kilowatt hours. How does a kilowatt hour differ from power? This is what normally shows up on your power bill. 1 kilowatt hour is the energy converted or consumed in 1 hour at the constant rate of 1 kilowatt, which is equal to 1,000 joules per second. So 1 kilowatt hour is 10 to the third watts times 3,600 seconds. Okay, we break it all the way down to seconds because that's our SI unit. So 10 to the third joules per second times 3,600 seconds gives us 3.6 times 10 to the 6th joules. Keep in mind, a kilowatt hour is a unit of energy, not power. The power is a watt. So, last example. Power delivered by an elevator motor. A 1,000 kilogram elevator carries a maximum load of 800 kilograms. A constant frictional force of 4,000 newtons retards its motion upward. What maximum power in kilowatts and in horsepower must the motor deliver to lift the fully loaded elevator at constant speed of 3 meters per second? Okay, it sounds complex, but let's take it apart and look at it here in pieces. You can see in the diagram We've got a couple of folks in the elevator. We kind of built our free body diagram over here. We've got the tension in the cable going up. We've got the mg, or the weight of the cart, and any contents down. And we've also got a frictional force down. So the mass is equal to 1,000 kilograms. The load is 800 kilograms. The frictional force is 4,000 newtons. And the velocity is 3 meters per second. So what's the maximum power in kilowatts and horsepower must the motor deliver to lift the fully loaded elevator at a constant speed of 3 meters per second? So we kind of go back to what we learned in our force relationship, or net forces. So the summation of the forces, all the forces in the y direction, are equal to, look at the free body diagram, tension minus friction minus the weight, mg, equals 0. Okay? We haven't introduced a moving object here. We are looking at just the statics. So if we rearrange the terms, the tension is equal to the friction plus the weight. So the tension is equal to 4,000 newtons, 4 times 10 to the third newtons, plus 1,800, the 1,000 plus the 800. So 1.8 times 10 to the third kilograms times the acceleration of gravity, 9.8 meters per second squared. So from that, we have a tension in the cable of 2.16 times 10 to the fourth newtons. So that's all of the tension in the positive y direction. So now let's look at power. We just said power is equal to force times velocity, and our force in this case is the tension in the cable. So the tension times the velocity. Well, we just solved for that tension. Okay, 2.16 times 10 to the fourth newtons. And the velocity of interest in this problem is that 3 meters per second. So 6.48 times 10 to the fourth watts becomes our power to satisfy what they've asked for at 3 meters per second. Now let's take power, that's 64.9 kilowatts. We just moved our decimal points around and rounded up. 1 horsepower is 746 watts. So watts and watts will cancel out. We end up with 86.9 horsepower is what it takes for the motor to deliver a lift fully loaded at a constant 3 meters per second. So that's all of Chapter 5. We've looked at work and energy. So now, more fun stuff in the next chapter: momentum, impulse, conservation of momentum, collisions, and glancing collisions. Let's have some more fun.